Now we can discuss some about the differences between classical and quantum network management. By and large, quantum and classical network management are the same. The various conceptual layering and FCAP model, they remain. And the non-functional attributes that I presented just on the previous slide also remain. The functional attributes remain for the most part, albeit they're adjusted slightly for the quantum domain. What I mean by this is at the EMS and the NMS layers, you'd expect it to be almost wholly the same. A classical network management system would, versus a quantum network management system, would be very similar at the EMS and network management or NMS layers. But the SMS layer, there'd be, of course, the domain-specific kinds of services I mentioned before, such as key generation as a service, entanglement as a service, or teleportation as a service. However, there are some differences that need to be considered. I'm going to go over each of these in upcoming slides. First, there's no physical topology discovery currently. In the classical networking world, topology discovery protocols have been developed in order to determine how ports are connected. LLDP, or the Link Layer Discovery Protocol, is the most widely used. By topology, I just quickly want to mention this is meaning how the various nodes are connected to each other, like there are various ports. If you have a device with 4 ports and different ports have fibers connected to them, connecting to different other equipment, the question is, what other port on the other equipment is this port connected to? And coming up with that topology is all those relationships is referred to as the physical topology. These protocols rely on ubiquitous presence of wave division multiplexing to convey the metadata. So already there was wave division multiplexing, and so adding another virtual channel for conveying metadata was easy to do. However, in the quantum networking world, fibers are generally utilized or fully utilized to convey the data, or the qubits, with no provision to convey the metadata. If it's not possible to convey the metadata in band, then an overlay classical network must be utilized to convey that metadata. In either case, agreement is needed amongst the quantum device vendors to achieve some form of physical topology discovery for optical networks. Next, there's the need for protocol adapters. In the classical networking devices went through a long period of needing protocol adapters. As each vendor had proprietary CLIs and a number of scripts were written to interoperate with those CLIs. And then SNMP, it did not get widely used. But now NetConf is firmly established in the classical networking industry, such that protocol adapters are now, for the most part, a thing of the past in the classical networking world. However, quantum networking devices being at a very early stage, it is understandable that manageability is a second concern. And so protocol adapters are again needed until that maturation occurs. Next difference is the need for stabilization delays. Some quantum devices require significant time to apply configuration changes. For instance, a laser may require up to 5 minutes to reach temperature. Needing to wait for the intended configuration to be applied is not new, but the wait time is an order of magnitude more. So 5 minutes is a long wait. Quantum orchestration systems managing such devices need to account for a stabilization when provisioning services in a timely manner. There's also another difference is the need to route timing signals the same as the photons. As quantum fibers typically only convey qubits with no wave division multiplexing, the timing protocol signals must be routed over alternate Ethernet cables, which may be either fiber or copper. However, some timing protocols rely on measuring the light transmission propagation delay, and thus must be routed over similar fibers along the same path in order to mimic the qubit delay within sub-nanosecond accuracy. Quantum orchestration systems managing timing modules Using such protocols must ensure that both signals are routed together. Another difference is the need to periodically calibrate polarization. Many quantum devices are polarization sensitive. They have, for instance, they assume the horizontal, vertical, diagonal, and anti-diagonal polarizations. Yet polarization can drift throughout the day. Environmental factors like temperature change can cause polarization to drift. Polarization maintaining fiber helps, but is expensive. Polarization compensators can be inserted into the data path, but they need to be adjusted periodically, for instance, once per hour. Quantum orchestration systems managing networks containing APC or automatic polarization compensating devices need to ensure that they are calibrated periodically. And this actually brings up an interesting point we touched on earlier about the utilization of the network. While certain services are up and running, there may be some capacity that's not being utilized, and while it's not being utilized, the system could, be, for instance, be calibrating the polarizers so that they're ready when needed.